Hi, I'm Martin, and I'm talking about approximate distance sensitivity oracles in subquadratic space. The setting of my talk is in fault-tolerant data structures, where the general theme in fault tolerance is that we want to maintain a graph property under edge failures. So in this example, we have certain pairs of vertices and shortest path between them. It might be that if some edge fails in that graph, that the distance between some of these vertices increase. And we want to prepare for that. The specific thing in the fault tolerance is that these failures arrive in batches, and we know their maximum number in advance. This is this sensitivity, denoted by a lowercase f. This is also the main difference to the decremental setting in dynamic graphs, where these failures may arrive one by one, but are potentially unbounded in numbers. Also in the data structure setting, we want to preprocess the graph once into a hopefully small structure that is then queried when needed. So in general, a query specifies a set of at most f edges and gets as answer the property of the graph g minus f, where the specified edges failed. And in this talk, we are interested in the property of pairwise distances between all pairs of vertices, or at least approximations of them. So the query would also specify a pair of vertices s and t, and would get as answer, we call it the replacement distance, so the distance between s and t in the graph g minus f. And the resulting structure is then called an f-edge fault-tolerant distance sensitivity oracle, or FDSO for short. As usual in data structures, we have many parameters, and if you optimize for some of them, the others get worse. So there's rarely a single best data structure for all use cases. The relevant parameters for us, starting with the sensitivity, so the number of supported edge failures, and by the way, in that top line above, I'm collecting the current setting so that it is also present on later slides. Another interesting parameter is the stretch. I said we are maintaining approximations, and we want the answer of our data structure to never underestimate the true distance, and also be at most a factor sigma away from the real distance, where sigma is the stretch. We do care about space of the data structure, which is measured in the number of machine words on log n bits. Also, we want the query time to be small. Of secondary consideration is the preprocessing time, so the time needed to prepare the data structure, but I can assure you, although I will leave it out in the statements for brevity, the preprocessing time is always at worst a factor of m, so the number of edges away from the space. What is very relevant again is what graphs do we support. For example, can we allow directed graphs? Can we handle weights and these kind of questions? And the special focus of this talk will be on space. Because if you look in the literature, you see that most solutions take at least n square space, so quadratic in the number of vertices of the underlying graph. And if you go to higher sensitivity, so if you want to support more than one or two edge failures, then usually that space blows up quite tremendously over quadratic. So we are in the ridiculous situation that for a data structure, we want to have a small structure, but in order to support all these failures, we end up blowing it up way beyond the space of the original input graph. And we want to mitigate that a bit in that we are aiming for DSOs in subquadratic space. Unfortunately, there is a reason why all these n squares show up, or at least there's quite a price to pay if you want to go subquadratic. Because Thorpe and Zwick showed that even if you're not supporting any failures, so if you're only reporting pairwise distances in your graph as is, if your underlying graph is undirected, then any oracle must have quadratic space or a stretch of at least 3. So if you are aiming for exact distances or near exact distances, you cannot make it in subquadratic space. Also, if your graph is directed, really you have no hope whatsoever for subquadratic space if your data structure maintains an arbitrary finite multiplicative approximation guarantee. you have to have quadratic space. So this is why going forward in this talk, I will only talk about undirected graphs. We are not the first one to ask that question of subquadratic space. We are aware of two different approaches in literature. The first one was given by Chechik et al. They designed an oracle for every positive integer k with stretch 8k minus 2 times the sensitivity plus 1. And they get for this quite a low stretch, this is quite a low space indeed. So if you pump up k, you can get arbitrarily close to linear. And they also have a quite nice query time that up to log factors scales with the sensitivity. The real problem with that approach is that also the stretch scales with the sensitivity. So if you want to support more and more edge failures, your stretch gets worse, which is not really what you want. The other approach is to use a fault-tolerant spanner. These are hopefully sparse subgraphs of the original graph G, such that if you fail the same edges in the spanner as you do in the original graph, then the distance between any two vertices S and T is at most the sigma times the respective distance you are looking for, the replacement distance. And if you store the edges of that spanner, you can think of it as a data structure. And if you use the current best construction by Bodwin et al., you get a very nice stretch of 2k minus 1 and the space that is even better than what Chechik et al. Had. But the issue with that approach is that currently we do not know how to query these spanners faster than running a single source shortest path algorithm on them. So for example, Dijkstra. So up to log factors, the query time scales with the space, and Bodwin et al. Also showed that this space is nearly tight. So there is a barrier for further improvement of space and query time in this approach. So what we want is designing an oracle that has subquadratic space, a stretch that is independent of the number of failures, and has a query time that is better than just running Dijkstra on a spanner. And this is what we got. For any parameter alpha and approximation parameter epsilon, for constant sensitivity and undirected unweighted graphs with unique shortest path, that means that between any two vertices there is exactly one shortest path. We can get DSO that has stretch 3 plus epsilon, so close to the Thorpe and Zwick bound, and this kind of space and this query time. So this alpha allows you to trade query time for space, where this notation here omits small polynomial factors in 1 over epsilon. So really nothing bad is happening in terms of epsilon. And you can trade this query time for space. So if you, for any constant alpha and constant sensitivity, you indeed get truly subquadratic space in this construction. But as I said, we are paying with other parameters for that, in that currently we are only supporting constant sensitivity. So if the sensitivity gets too large, we converge to quadratic. And also currently we cannot handle weights, so unweighted graphs only. But in another result that will appear later this summer, we addressed some of these shortcomings already. With different techniques, we now have a sensitivity up to little O of log n divided by log n, and we can handle weighted graphs. We get a stretch versus space trade-off that is only slightly worse than doing the spanner, but here the issue is that we have a very high query time, where we had an arbitrarily low polynomial query time. Here we get something that is always at least linear, but at least it is better query time than just running Dijkstra on that spanner. For the remainder, I will talk about how we achieved this result. Our techniques are based on the DSO by Chechik et al. They had a stretch of 1 plus epsilon, so near exact distances, and therefore, of course, had a quadratic space, and at least for constant sensitivity, a very good query time of polylog. So how did they achieve that? They built a so-called fault-tolerant tree, or FT tree for short, for every pair of vertices. This is where this n-square factor comes from. And what it is an FT tree, if you query the FT tree that is associated with your pair of vertices, it gives you the exact replacement distance. If the shortest ST path in G minus F satisfies some technical condition, I won't go into details here, but the query procedure then essentially tiptoes around this condition. This is where they lose this slight stretch slack to 1 plus epsilon. The main issue really, if you try to make this work in subquadratic space, is the large number of fault-tolerant trees. We cannot afford to build an FT tree for every pair of vertices. So what do we do instead? We use a paradigm that is quite common in fault tolerance, in that we define a cutoff parameter L, and we sample a uniform set of n divided by L vertices. And with Chernoff bounds, you can then show that with high probability over all queries, if the true replacement distance is larger than your cutoff parameter, then the shortest ST path in G minus F, so the replacement path you're looking for, is hit by some of those sampled vertices with high probability. So essentially you can use these sampled vertices to stitch together solutions from small paths into longer paths. But yeah, we do this by these FT trees, in that we build these FT trees only for those vertex pairs that have at least one sampled vertex in there, and this is where we save something about quadratic number of trees. What I completely sweep under the rug here is how to get these FT trees to work in subquadratic space. This needs a deep dive into the techniques of Chechik et al. In this Soda 17 paper, and you really in every stage have to check can this be done in subquadratic space, and if not, how to work around that. But I don't have the time to go into details here in this video. Also, it creates the need of a separate solution for small distances. I said we use the FT trees to stitch together small paths into longer ones, but then we need a separate solution for small replacement distances. Also, you have to be a bit clever in the stitching, because otherwise your query time scales with the number of sampled vertices essentially, and we use the careful resampling approach and some additional techniques to bring this down to something that depends only on L and F. And if you then do the math at the end, you end up with a cutoff parameter of roughly n to the alpha divided by f plus 1, where alpha is this parameter the user can choose, and this gives you this amount of trees, and this is also exactly the term that showed up in the space statement of the theorem. Also, with this improved query time, you get an n to the alpha query time, so a low polynomial for the query. For the rest of that video, I will mainly talk about what we did for small distances, because I feel that is most useful also for other researchers, because that is actually a quite common thing in fault tolerance, that you do the sampling and end up with trying to do something for small distances and stitching together for long distance. So it's a quite common task that you want to design a DSO that is only supposed to give the correct answer or a good approximation if the real replacement distance is smaller than your cutoff value. The standard solution in the literature for that is to use Wayman and Euster graphs. They suggested to create L to the F copies of the original graph G, and in each one of them fail any edge independently with probability 1 divided by L. And what they then showed is that with high probability over all queries, there is some copy that does not have any edge of those that are supposed to fail, but all edges of an ST replacement path, in that the ST distance in that copy is the actual value you're looking for. And what they then do is go over all these graphs, check are there any edges of F present, and if not, record the ST distance, and the minimum recorded distance is then with high probability the value you're looking for. This raises the question whether we can find the correct copy more efficiently. And also we want to use this solution for small distances in our oracle for large distances in subquadratic space. And for this, the original Wayman and Euster graphs are too large because they essentially scale with the number of edges. And if the original graph is too dense, we would run into quadratic space again. So what do? We essentially put the whole sampling process on its head and build a whole sampling tree that is guided by that height parameter h that will soon help us to get some trade-offs. How do these trees look like? In the root you have an empty graph, so no edges present whatsoever, and every inner node has L to the F divided by H children, and each child takes all the edges of its parent and reinsert any edge of the original graph with this probability. So we are not failing any edges, we are reinserting them. Of course, for the children in the first level, there's nothing to inherit, but further down we really take the present edges and additionally add all other edges with this probability. And if you do the math for h plus 1 levels, you get slightly more nodes than what we had for the original Wayman and Euster graphs, and more importantly, down in the leaves, all the way down, any edge has the same probability to occur as in the original Wayman and Euster graphs, but we are losing independence in that if you take two different leaves of the sampling tree, they at least have all the edges in common of their lowest common ancestor. But this is actually where we get our saving from, that leaves that are nearby are highly correlated. And how do we exploit that? So our query, when tasked with the query set f, starts in the root and follows in each step to any child node that has no failing edge. So the first child we find that does not have any edge of f, we go down. So we try to reach a leaf in a depth first manner. This takes this amount of time, so number of children to evaluate in each level and O of H level. And all of this is held together by showing that once you reach a leaf in this way, you are in the correct copy with some exponentially small probability, but it is exponential only now in that height parameter. You can get rid of all the dependencies on L and F. And if you then do this in sufficiently many independent trees, you get to have the right copy with high probability. So really where you save something is that you can recurse on the first child you see that does not have any edge and try to reach a leaf quickly instead of evaluating all the leaves of that sampling tree. And if you optimize for that high parameter h, you end up with something like square root of f times the logarithm of that cutoff value L. And this gives you L to the little o of 1 trees. And more importantly, a super fast query time of also L to the little o of 1. So much faster than evaluating all leaves or all Wayman and Euster graphs. Problem remains is that if your original graph is sufficiently dense, then also this whole construction takes more than quadratic space. So what do we do to make the whole thing work also in subquadratic space? Again, currently we have exact distances and we were very willing to trade some stretch for lower space. So in the lowest level of those trees, in the leaves, where we are only interested in the distance between S and T, we replace these graphs with Thorup and Zwick distance oracles. So no sensitivity here, it's just oracles to report pairwise distances. and they have a very good stretch versus space trade-off and very good query time, especially if you're only interested in constant values of k. And in all the inner nodes of that sampling tree, we use the edges only to make the decision in which child to recurse. And we show that if you use a certain kind of spanners, so not exactly the Thorup and Zwick spanners, if you're familiar with that work, but a slight variation of it, you can make these decisions reasonably well. And that brings the total space of all the sampling trees down to this value, which is truly subquadratic. So in summary, we gave a distance sensitivity oracle for constant sensitivity with stretch close to the Thorup and Zwick bound and subquadratic space, and a low polynomial query time. And for small distances, we get some new solution with a stretch versus space trade-off and a super fast query time of L to the little o of 1. So what is left to do is essentially we want low polynomial is nice, but what you're really aiming for is a polylog query time. And also our DSO is currently not supporting weighted graphs. So we want to make this kind of or even better query time work with weighted graphs. And with these words, I thank you for your attention.